can have the status in future. We start basically with me. I'm not an electrical engineer. I have a physics degree from Mainz University. I spent 14 years at the European Laboratory for Particle Physics. To be honest, physics was a bit of an alibi for me. I was spending most of the time, starting with my diploma, with data acquisition and control systems. Already at Geneva, I started to work with CAN and particularly CAN-Open. I had been chairman of a couple of working groups there. Then starting 2019, I had a 5.5 years break with CAN and CAN-Open, doing mostly Ethernet IP, but again, back to the same field, control systems, industrial communication. And now, since 1 year, I'm back in the CAN world with CAN and Automation as a technical manager. I oversee the specification work, so basically all the specifications that we create, including a few international specifications, end up on my desk for a final review. So what is CAN and Automation? What are the objectives? It's an international users manufacturers group that develops and supports particularly CAN-Open and other CAN-based higher layer protocols. Was founded in 1992, basically to provide CAN-based technical product marketing information. We see our aim in fostering the image of CAN technology and basically provide a path to future network technologies. So history or milestones, as mentioned before, in 1992, the non-profit CiA association was founded in German. It's EV is eingetragener Verein. Also in 1992, there was the first CAN newsletter. The first international CAN conference was in Mainz in 1994. It was the time when I was still in Geneva. The first edition of the CiA 301 specification, the CAN-Open application layer and communication profile, was published in 1994. In 2000, there was the CiA GmbH limited company as a commercial branch of CAN and Automation, basically to do specification sales, to technical testing, so conformance testing, to training, everything which is really more oriented as a commercial towards a commercial effort. Then in 2012, basically the main topic of our session of today was first presented at the International CAN Conference in Hambach Castle in Germany. It was actually a very nice event. And then end of 2018, the first CAN XL meeting was organized. Basically, it was a technical proposal to extend the already increased data field that was started with FD from 64 bytes to 2048 bytes. We will address CAN XL only very briefly today and not put the focus on that one. So member distribution, essentially, there are around 80 members in North America, Northern Europe around 70. Most of them are actually located in Central Europe, and most of them actually in Germany. Eastern Europe, 20-something, Far East, around 60. Southern Europe, mostly actually Italian, so a large part of that is Italian, around 70. Rest of the world, 40 members. Even in Qatar, we have recent members. So from the business categories, most of them are device suppliers, so that actually manufacture, for example, CAN-Open devices. Subsystem manufacturers, service suppliers, technology enablers, for example, companies that write protocol software, tools. Then there's a few research institutes, actually even CERN, where I was, is a member in CAN and Automation. That's why I got in contact with CAN and Automation. So I knew the founder of Canon Automation since around 1997. And solution providers, so services also. And we have end users. So just simple end users that are not affiliated with a particular company, just joined Canon Automation. Structure concerning a board of directors. There's a general assembly. There's a business director as Christian Schlegel, currently from Christian Schlegel Consulting. A manager director, which is Holger Seltwanger, then a technical director, which is currently Magnus Hell from Infineon. And then there's the CiA GmbH, which is basically run by CEO Reinhard Zitzmann, who once in a while does these seminars as well. Below these committees, the technical committee and the business committee, there are first of all 5 elected companies. It happens to be that they're all basically the same in a sense: Bosch, Emotas, ESD. ESD I know also since 27 years, microcontrol, and Vector as well. So from the organization of the technical groups, essentially there's a technical committee, and then there's interest groups. We have currently 7 here on the slide. There will be an 8th one inaugurated next Tuesday, I think. We will come to that later. And below each of these interest groups, there are special interest groups or task forces. Currently, actually, the most active one is the lower layers interest group, and the safety and security interest group. So basically, bringing or updating the CANopen safety specification. That's one of the groups, and actually making sure that Canon-based protocols are fit for the security requirements of the future. Standardization. So Canon Automation not only works on the CiA standards, but also participates in the international standardization efforts by DIN, by ISO. ISO, and particularly the 11898-1 and -2. They both have been published in the most recent edition, the 3rd edition last year. But 11898-2 is currently under review. There will be a 4th edition published, which I'm doing the editing on, most of it. And I'm not sure if we still get it out this year, but it should be within next year. There will be a new edition of part 2, correcting some of the errors that had been identified in the 3rd edition. So there's another thing that I'd like to, and I think after the next slide, we're done with the introduction. And we come to the actual topic, CanFD. There's a technology session, technology day. The day is missing here, with focus on CanOpenFD on the 3rd of April in the afternoon. Again, language is English. Participation is free of charge, but there's a mandatory registration, basically to get the login details, the Zoom details. So please contact events@can-cia.org for details. The program will be actually an introduction to CanOpenFD, which is done by Canon Automation. Then there's CanOpenFD device design by Emotas. Dynamic node and network addressing, again by Canon Automation. There are small coffee breaks in between, so you can get something to drink. Electronic device description, system design recommendations, integration of CanOpenFD systems into the cloud. And then there's a concluding presentation, so a final presentation on cybersecurity and CanFD-based applications, CanOpenFD-based applications, which is held or run by Embedded Systems Academy. So further webinars. So we have the CAN FD status in the future, actually now. Then there's a functional safety and can open webinar in June. Lift network design in October, sorry, excuse me. Cybersecurity is on in November, and network XL network design. There will be a session in December this year. Basically, the idea is you get a bit more detailed information about the technology rather than what we can do now within this 45 to 60 minutes. So, CAN FD status and future. We start now. So, the history. CAN is actually quite old. Yeah, started in 1982, Bosch internal development. There was the first public presentation of CAN, Controller Area Network, as an SAE Congress in, I'm not quite sure if it was in Detroit, but in 86, so long ago, close to 40 years ago, time flies. In 2003, the first edition of the ISO 898-1 and -2 standards were published, the data link layer and the physical layer. In 2011, the development of CAN FD started again at Bosch. It was presented, as mentioned earlier, at the International CAN Conference 2012 at Hambach Castle. The development continued up to the publication of the second edition of the ISO 898-1 and 2 in 2015, respectively 2016, and the first ISO-based FD implementation. Between 2012 and 2015, there were earlier CAN FD implementations, also in hardware, actually, by some of the hardware suppliers that are not 100% compatible because somebody figured out that there was an error in the initial Bosch specification in the CRC calculation. But now everything is fine. And yeah, so you will be surprised that it is actually not necessarily visible. We will talk about that later in the industrial automation, but pretty much every microcontroller now contains a CAN FD controller, not a classic CAN controller anymore. And actually, pretty much everywhere in the automotive industry, you find in vehicle networks up to, yeah, I've seen up to 8 CAN FD, individual CAN FD networks. In 2018, there was the start of the CAN-XL project, and basically in 2021, there was the first release of a CAN FD Lite specification, which at that time was a CiA specification. Now it's included in the annex of the ISO 898-1 third edition. I haven't seen personally any implementation or application yet, but again, this was driven by the automotive industry. So we come to that towards the end of the presentation. So the requirements, initial requirements, which are still pretty much valid. It's a broadcast message transmission, so you not send a point-to-point from one node to another. CAN is inherently broadcast. So basically, the other thing is you identify a message, not necessarily a node. So each message gets an identifier, and basically the receiving nodes decide if the message based on this identifier is of interest for them. It's a multi-master bus access, not that everybody talks at the very same time, but in a non-destructive arbitration scheme, basically when multiple nodes start transmitting at the same time, they figure out who's got the highest priority, which again is based on the message identification. So it's a non-destructive bus arbitration. Prioritized message identifier, which is used by the arbitration. It has a very sophisticated error detection. So basically, either everybody sees the correct message, or basically the message is falsified or invalidated by a particular station that doesn't understand it. So it's invalid for all of them. So automatic transmission of faulty messages, and there's a fault confinement. So basically, if one device, one node on the network goes into error states, it stops transmitting and is not disturbing the bus anymore. So in terms of the OC model, the ISO OC model, basically what we discuss mostly today is located in the data link layer and the physical layer. So the data link layer is essentially 898-1, and the physical layer is largely 898-2. So particularly the logic link control, media access control is in part 1, and the rest is in the document. So what you have in classic CAN communication as services, essentially the possibility to transmit a message. As mentioned before, it's a broadcast scheme. So you have one producer, CAN message producer, that gets a sort of a request from any of the higher layers in the OC model. And you can transmit up to 8 data bytes, and you have multiple consumers. You have also the possibility with classic CAN to request a transmission of a particular message, which is again identified by the message identifier. And then the owner of this message, or the producer of this message particularly identifier, sends basically the corresponding data frame out to one or multiple stations. So this, first of all, implies that a particular message identifier is owned or used only by one particular node. So when you send out a request, let's say to send out a message with the CAN identifier 500, just for fun, and multiple stations would be producers of the CAN identifier or the message with CAN identifier 500, then you would soon end up in error states, with the exception that each of these owners, well, there is technically an exception in one of the protocols in CAN Open, if each of the producers would send exactly the same message. So let's say 500 would be a particular message that is a confirmation for requesting a device internal service. So one can request it, and each and everybody sends it out with exactly the same data. Then you don't run into error states. The lower part, this remote frame requests, is not particularly popular anymore, and it's discouraged from use. So how does that look like? Essentially, you have one device which is a producer of a frame of a message, sends it out on a bus. Consuming stations just receive this and filter it, and depending on the filter settings they forward the message to the local intelligence. Essentially, this is typically then the device application. I dropped the picture that shows that for remote transmission requests from the presentation, because as said, it's currently discouraged. So we're not going to go too much into detail about the particular bits and bytes in there, but essentially, when you look at the frame formats, there's something I just see wrong in the upper frames. The surrounding frame is a bit too long, but you have the arbitration field, you have a control field, you have a data field, a CRC field, acknowledge, and an end of frame. The arbitration field is essentially this message identifier, plus here in this particular case, the remote transmission request bit. We have two options: the base frame format, which uses an 11-bit identifier, and an extended frame format, which would then use a 29-bit identifier, which it's been mostly used by, for example, SCE J1939 in truck networks. Industrial protocols that I know of, they support, at least CanOpen, for example, would support 29-bit identifiers. I haven't really seen an application, but we will come back to that at least in the discussion session later on. The disadvantage of the 29-bit identifier is basically the identifier is longer, so it's 20-bit times longer, which again is affecting the latency time. So the idea of this short data field of just 8 bytes at most at the time was that you have very short messages and have low latency when you, for example, lose an arbitration and have to retransmit when the bus is free again, that the latency or the delay before a message can be retransmitted is not too long. So the control field is pretty much identical. You have mostly this 1-bit, the identifier extension indicating that there's a 29-bit identifier. Otherwise, in the lower, in the CE, we can extend frame format. It's a reserve bit. And then you have 4 bits which contain data length code. So essentially, you count, when you look at the next slide, from 0 to 8. So the data field can, for CAN CC, and actually also for CAN FD, be of 0 bytes length. And for CAN CC, it can contain at most 8 bytes. So this poses a bit of a problem these days. It was perfect in the early days of CAN, but currently, particularly with respect to security, we will see later that we have a problem there. So what is there as in the field of higher layer protocols? We have, first of all, from Canon Automation is CanOpen, which is the most recent version. It's from 2011. It's pretty valid still. It's the CiA 301 specification 4.2. CanOpen application layer and communication profile. There's a huge installed basis of devices, which also, again, poses a bit of a problem because people try to stick to what they have and what they know. Then there's additional application layer functions, essentially specifying network startup. So basically master behavior. It specifies program download, which has been largely used actually for example, firmware updates. There's one of the volumes is focusing on redundancy, so cable redundancy and network at that time was called master redundancy. And then there's, I haven't listed them, because it would be too long to read them actually, a long list of device profiles. So from I/O devices, encoders, drives, whatever you like, hydraulic functions, very special functionality like medical devices, so injectors, you name it, subsea devices, a lot of things. From ODVA in Ann Arbor, there's the CIP networks library, first of all, which is Common Industrial Protocol that which kept me busy a bit between 2019 and last year. And then there's the CIP Networks Library Volume 3, the DeviceNet adaptation of CIP. There are multiple protocols, so ControlNet, CompoNet, Ethernet IP, and DeviceNet, which all use the base CIP Volume 1 document. From SAE is also a long series. There's the On-Highway Equipment Control and Communication Network, as I mentioned, J1939. Which uses the 29-bit identifier. DeviceNet uses 11-bit only. As I understand, DeviceNet is not really maintained anymore. The last revision of the specification is a couple of years old. ODV now focuses on Ethernet IP for the industrial automation. So a summary on CAN-CC to conclude that part. It's an 11-bit or 29-bit message identifier. There's a possibility for remote request frame transmission. It's up to date 8 data bytes per data frame. There's a Hamming distance, basically, which gives you an idea about the quality, the error detection capabilities. 6. You can basically have local failures, but they are globalized. So when one device detects an error in a message, for example, CiA error, it's announced or indicated globally. So each and every device in the network gets the same information. There's a quite low probability of undetected faulty messages. There are error counters for independent error counters for received and transmitted messages. When you get to high, you essentially switch off your transceivers. And the number of nodes is not necessarily limited by the CAN protocol. It's clearly limited by physical aspects, bus load, for example. And there will be, typically there is a limitation of number of individual nodes that you can have on a network introduced by the higher layer protocols such as CANopen or DeviceNet. So this is the part on CAN-CC, quick introduction. Now we come a bit to essentially the current status. As indicated earlier, was at the beginning of the presentation, CAN was driven not necessarily by the industrial automation industry, but by the automotive industry. So that's where the short messages come from. So networks in cars or in vehicles have changed over the time. So from just plain network of orientated structure, you now in cars you find largely domain-oriented networks. So you have something that integrates CAN, Ethernet, FlexRay, and LIN, and they're running via gateways, basically in one and this in a combined network, but individual networks. Here in this particular picture, for example, you have here a central car unit, a central car gateway, then CAN Ethernet technology, which is now frequently actually Ethernet all based, single wire Ethernet. Then you have your CAN networks, and below there you may have LIN technologies. You see the evolution, and okay, excuse the X because I haven't gotten any more recent data. There's certainly a more recent one. I owned once one of those things on the right side, the W211. You see the number of electronic control units. So they increased drastically, factor of 10 basically between the first car that had a CAN network, the Mercedes S-Class in 1980, which was produced in 1984. And nowadays the 212 and 213 quite likely has even more, or the more recent ones, 214, even more. And the number of messages that you see inside an in-vehicle network also drastically increased, from fewer than 100 to 6,000 and above. So again, there are much more requirements, higher requirements on the in-vehicle networks now. And when you look at the far left here, I suspect that this thing just had analog wires, no intelligence at all, apart from the driver. So requirements in the automotive industry, higher bandwidth, particularly also for software download, because diagnostics, higher throughput, additional functions. So basically, when you compare a car from the 80s with a car from now, you will find there's a lot of functionality in there. If you like it or not, I sometimes don't, but it's there, that has not been dreamt of in the 80s. Yeah, so you have so many assistance systems in the car now that require more and more network functionality. The other end is basically the reliability needs to be maintained. That's a given. And people would want it. Actually, it's funny enough, it's still like to keep the known technology to some extent, because you have to train staff inside the factory, inside the workshops, basically. And that introduces a cost factor, which is not insignificant. Then again, hardware, which actually includes wiring, which can be quite a lot inside cars. And the physical layer needs to be as robust as for CAN CC. So on the bottom right, you see a glimpse of what has been done with CAN FD. With CAN CC, you had something in bit time synchronization. This has to some extent been given up with CAN FD. So here the idea was that you maintain the in-bit time synchronization at what is called nominal bit rate for the arbitration phase and parts of the control word phase, and then switch to free transmission inside the data phase. So first of all, not only the data field size itself got extended to 64 bytes, but also the transmission got accelerated by just dropping the in-bit time synchronization. So you have the arbitration phase, which you can have up to between 50 and 1 megabit, 50 kilobits and 1 megabit. Then you have the data phase, a free transmission. So the speed there depends a bit on the physical layers. And the acknowledge phase, again, which switches back to the nominal bit time or bit rate between 50 kilobits and a megabit. This screenshot, I think, is coming from Bosch, one of the early presentations. You see here the arbitration, the data transmission, the data phase, and again, what comes afterwards, acknowledge phase. So they tried at the time 15 megabits or succeeded with 15 megabits and 500 kilobits for the arbitration phase and acknowledge phase. Realistically, in cars, the data rate is not at 15 megabits because they need that, or still have the need for the reliable physical layers. And within cars, the conditions, the environmental conditions are not necessarily like in the laboratory. So you may once in a while have outside temperatures higher than 22 degrees Celsius or lower, depending the time of year and where you are. But on the other hand, when you go, for example, to 4 megabits, just by increasing or going from CAN FD to from CAN CC to FD from 500 kilobits to 4 megabits, you see already data throughput which is quite increased. And the same comes when you see the size of basically you had 8 bytes limitations before, and now you have 64 bytes. Combined, you get significant performance improvements, and basically all cars now are based largely, at least for the current part, on CAN FD networks. So from the communication services point of view, you have, as mentioned earlier, a data frame, which can now have anything between 0 and 64 bytes data content. There is still, given the compatibility to some extent between CAN CC and CAN FD, you can theoretically request a particular message ID, which is configured as a CAN FD data frame, with a CAN-CC remote transmission request, but it's, let's say, discouraged. You should really refrain from using remote frames anymore. However, the 29-bit identifiers that were originally introduced to the classic CAN in the 80s or used there is still supported. So when you compare now basically the base frame format, classic base frame format with the FD base frame format, you see here you have a data field of up to 8 bytes. And here you have up to 64 bytes. You run at a higher bit rate. And you have somewhere in the control field a field which is called bitrate switch, and a sample point, basically where you detect your, pick up your signal. You say, okay, now switch to the FD data bit time, you increase speed. Arbitration field is pretty much the same as for CAN-CC. Control field has changed a bit because we have the FD frame indicator, and the bitrate switch is there as well, which was not available for the CAN-CC format, and an error state indicator. Again, the data field, it is optional, it can be 0 bytes. CRC has also been changed, essentially depending on the size of the data field. You have either a 17-bit CRC or 21-bit CRC. So with that, given that, sorry, let me just go back. The DLC field still is limited to 4 bits. So you can count technically up to 15 with 4 bits. But as we need somehow to identify 64 bytes fields and indicate 64 byte fields, what was done with the basically the 2015 ISO specification, that you introduce a granularity. For example, you count regularly as before up to 8 data bytes with byte granularity, and then you get in chunks of 4 bytes, 8 bytes, or 16 bytes up to the 64 bytes. So now let's have a word on the higher level protocols. There's, yeah, I don't know, call it a problem, but basically what many higher level protocols do, that they don't make a clear distinction between network and everything between network and application layers. So this was already for CAN-CC the case. You have the data link layer, the physical layer, and then you have an application layer. And on top of that, there sits the application device profiles, for example. It's pretty much common. Even at TCP/IP, there's not a clear distinction between, for example, application layer, presentation layer, and session layer. So, CAN OpenFD. So I was the chairman a couple of years ago of that group. It's specified now in the version 1.10. It includes much more flexible, what is called universal SDO service. So it's SDOs is a classical service data point to point from one client. You connect to one server and then transfer your data. Universal SDO allows broadcast, which is very interesting when you want to download, for example, firmware to multiple devices at the very same time. It allows for network routing. It introduces session IDs. Emergency messages have been extended. And then there's the 1302 series, which is still in preparation, additional application layer functions, which, for example, again, introduces or specifies manager startup. It's now called manager, not master anymore. The program download, which had been sort of abused for the bootloader functionality, has been taken out there, and it is now in a separate document that is about to be published in about a few weeks. So there's a final draft for proofing available within CiA and the task force. So can OpenFD, it admittedly hasn't been the success that many people had hoped for in the industrial automation area. It is used, however, in machine internal networks, where you don't see that there's actually kind of OpenFD in there. There's only a few commercial devices available. And in the industrial automation, there is honestly a strong competition by industrial Ethernet solutions. However, with CANopenFD, we still benefit from the technological concepts of CANopen, so everything which is valid for CANopen. So basically, skills, that you had to teach your staff and is still available there. And there are calculations, again, driven a bit by the automotive industry, that CAN networks still offer better latency than, for example, single wire Ethernet. So that concludes a bit about the current status. And now we come to the big topic of these days. You quite likely have all heard of that in Europe already, at least, there's an institution called EU, which has published in 2019 a Cybersecurity Act, which is now entered into force. Is very vague. The only thing that it essentially does, it gives a permanent mandate to the European Agency of Cybersecurity, European Union Agency for Cybersecurity, is based in Athens, in Greece. And it sort of introduces a uniform certification framework for ICT in industrial communication and telecommunication products, services, and processes. So it's, I'd say, theory. However, end of last year, there was that part that makes people nervous nowadays. There's the Cyber Resilience Act, and that is puts much stronger requirements onto all parties involved. That's software providers, device suppliers, system integrators. It's entered into force, so it's become official. It's published in December 11th, 2024. And the requirements of the CiA have to be complied with December 11th, 2027, which is not too far away, which makes people nervous. So there are discussions about what does this Cyber Resilience Act actually imply. Some people say it's applicable only for new products, but that you bring out on the market. And some people say, no, it is not actually bringing out a new product, but selling a new instance of an existing product. There was a presentation last week at Embedded World by Professor Niemann from University of Applied Science from Hanover, basically stating that it's new instances of existing products that have to comply by December 11th. Okay, admittedly, he presented this with the view of Profinet in mind, but it applies to pretty much everything. It will apply also to CAN-based networks. Inside the preamble, you find a statement basically that outlines already what you have to do. You have to design and develop in accordance with the essential cybersecurity requirements laid down in this particular regulation. So it's not just that you, at the end of the day, you have to test it, but you have to start the design and development already with the regulation, the requirements in the regulation, which particularly makes people nervous because it introduces a huge development on documentation, particularly documentation effort. So you have, similar to safety, document pretty much everything. So it's not only affecting industrial automation, but also the automotive industry, and they are the main driver behind certain proposals now, because you have security requirements that are also applicable for CAN networks in cars. So most of the CAN networks in cars, okay, Ethernet networks taken off, but the CAN networks are CAN FD technology. And there's a proposal which will end up, as I mentioned straight at the beginning of the presentation, in a new interest group, which is inaugurated next week. So proposal is essentially to use Ethernet frame and put it into small chunks of 64 bytes and transferred via the CAN FD network. Again, having the advantage of the low latencies and performance reasons. And you have the cables inside the car. Cables are a significant investment. So there's the interest group will be quite likely called Ethernet over CAN. And currently it has CAN FD networks in mind, but there are also competing proposals for CAN XL networks, because with XL you have 2048 byte data bytes. It's much easier to put an Ethernet frame in there, but CAN XL physically in cars is quite a bit away still. So CAN FD is reality. So for CAN CC, yeah, it's pretty obvious that there's a limited size of the data field and bandwidth. So what can you do with in terms of security on 8 bytes? On the other hand, there's the strong interest that we have CAN CiA higher level protocol cybersecurity interest group or special interest group. They say everybody has a huge installed basis. We would like to reuse our existing devices and, if possible, just changing the software. Personally, I suspect that will not work, but this is an ongoing discussion and there's a lot of effort in there. What you have, and you see that in the next few slides, a bit of process data, protocols. You have process data, service data, network management. Typically, network management is very tricky or susceptible to security, because you wouldn't like to allow somebody without authorization to reset the network. Everything like that is specified in the application layer. And this would, particularly for both the CiA 301 specification and the 1301 specification, enhancing the current application layers and communication profile specifications. So what do you do here? Service process data, CC, very difficult, 8 byte. 64 byte, I will show a picture that I've taken from a presentation last, I think it was October. You can do that with CAN OpenFD. 64 bytes, you can have limited security support, but at least it's currently demonstrated that it will to some extent work. There are prototypes implemented. The idea is also, instead of using the 11-bit identifier, just go using these additional 18 bits available with the extended identifiers for industrial applications. Service data, when you exclude expedited service data, so there you have just 4 bytes of, at most 4 bytes of data, but for domain data, for example, for firmware data, which is typically a domain of a couple of kilobytes, 10 kilobytes or something like that, you can include definitely security information, similar as with Ethernet frames, with a proper integrity check value at the end of the thing. So this is also one of the things that is definitely required, that you don't download invalid or illegal, let's say, firmware. Network management, they're kind of typically short, so you should have a possibility to add some sort of authorization or integrity value at the end in CanOpen. The classic was just 2 bytes. So you have limited possibilities, but they are still there. Initial conclusions for CAN security. So it will be difficult to do it for the current CAN-CC-based industrial protocols. That might be a motivation for those people migrating to CAN-FD or CAN-OpenFD. There you can do something. We will have to amend the specifications. Particularly for CAN-CC, it may not be possible to secure all protocols without compromising system performance. But there are demonstrators that integrate security concepts into CAN-OpenFD. That is a picture that I've taken from a presentation by the Institute für verlässliche Embedded Systemkommunikation in Offenburg, Applied University of Offenburg. So where you have a certification authority, a credential entity, and you can do that also embedded. Here they use a Raspberry Pi, and then you have managed CAN-OpenFD devices. Again, this is CAN-OpenFD, not CC. So it might be, this is heavily worked on currently, and there we have a meeting of the higher layer protocols cybersecurity group again on 2nd of April, as far as I recall. So then we come a bit to the future. There's no technical details in here yet, and it's only just a very short part. Even as CAN-FD, things move ahead. So you had a network-oriented topology towards a domain-oriented topology. Nowadays, the latest and greatest concept is zone-oriented topology. And basically, within the zone, you have multiple network topology technologies. But you may have quite a big number of devices inside some of those networks. So there was this concept of CAN-FD Lite, and Lite has a double meaning again here. It's Lite, so it's sort of a subset of the CAN-FD functionality, but it is also Lite because it may be used, or that was the initial application, to use LEDs inside the cars, because you have now plenty of those. So in their huge numbers. And the idea is that you have a simpler commander-responder scheme. There's no responder-to-responder communication anymore, as you had with CAN Classic, CAN-FD. So one commander controls the communication that resides in the light in the body control unit, and responders only react. This again, light actuators, small devices, a light source, for example, but light also in a sense of not heavy. So you have a high bandwidth, and there have been numbers that are found that you can have 1 megabit networks that control up to 4,000 individual LEDs. Is a busline topology based on CAN-OpenFD compliant transceivers. Responders can share the same transceiver on a PCB. So the main motivation was to be cost effective. It's a subset of FD. Responders are synchronized to the commander. No responder-responder communication, no arbitration, no error frames. Basically, you just ignore error, and no acknowledge bit. Lightweight implementations of CAN-FD. There's still a lot of open issues. There are working groups very active, higher layer protocols, request response. There is still worked on, and for example, system design conditions are still discussed. So, a summary. CAN has enabled successful network implementations in both automotive and industrial applications. Payload and performance limitations resulted in the development of CAN-FD, which is pretty much to be found in each and every microcontroller nowadays and in cars, widely used in the automotive industry. In the industrial automation, it has not yet widely adopted. However, the security-related regulations may drive a shift to CAN-FD also for industrial automation. Again, there's a quite active working group where I like to invite all CiA members to join. Particularly, we are lacking a bit of system integrators that formulate their actual requirements there. And there are proposals to enable security for CAN-FD networks in vehicle networks, basically using technology that has been taken over from Ethernet, MACsec, and particularly in different approaches there. But this is still under discussion also. So I think that concludes the presentation just in time. And now we'll have a bit of time for questions and answers that if I can give them to you. There is already one. Can CC and FD exist on the same bus? I think I mentioned earlier, you don't have these remote transmission requests anymore for CAN-FD. There's no frame format there available, but you technically, even if it's not recommended, can send a CAN-CC remote transmission request and get a CAN-FD answer. But it depends on your system configuration. Then I would like to thank you again for attending the meeting, the webinar.